The next set operation that we'll talk about is the Cartesian product. So let A and B be sets. The Cartesian product of A, denoted by A cross B, is defined as follows. A cross B is the set of all ordered pairs A comma B, such that A belongs to A and B belongs to B. So all the ordered pairs whose first component comes from A and whose second component comes from B. And I just want to pause here and note that the term ordered pairs is telling us something, which is that the order matters. The first one comes from A, the second one comes from B. It's not the same as if I did B comma A. And we know that we're familiar with ordered pairs from our algebra classes. So here are some examples. Let A equals 1, 2, 3, and B equals 4, 5. Then A cross B is the ordered pair 1, 4, the ordered pair 1, 5, the ordered pair 2, 4, the ordered pair 2, 5, and so on. And we can note that the cardinality of A cross B, in this case, is 6, which is equal to the cardinality of A times the cardinality of B, 3 times 2. Or we could also have done A cross A. So you can cross a set with itself. And here we see that we'd have 1, 1, then 1, 2, then 1, 3, and so on. And the cardinality of A cross A is 9, which is the cardinality of A times the cardinality of A, or the cardinality of A squared. So from this, we see the general rule, which is that if A and B are of finite cardinality, then the cardinality of their Cartesian product is going to be the multiplication of their cardinalities. Similarly, we could define the Cartesian product of 3 or more sets. So if we had 3 sets A, B, and C, then we would have ordered triples instead of ordered pairs. The first element coming from A, the next element coming from B, and the next element coming from C. And when we're taking the Cartesian product of a set with itself, it's common to use this exponential notation. So it looks like A squared, but it's the Cartesian product of A with itself, or A cubed is the Cartesian product of A with A with A, and so on. Another definition we have here is the definition of the power set. For any set A, the power set of A is the set of all subsets of A, and we denote it with this script P of A. So we already know that a set is just a collection of objects, and now we have the power set is a set of sets. So here are some examples. Perhaps the simplest example is the power set of the empty set is the set containing the empty set, because the empty set has only one subset, and that is itself. So the set of all of its subsets is just the set containing the empty set. Or if we had a singleton set, like 1 here, the set that just contains the element 1, then its power set will be the empty set and the set 1. Similarly, for this doubleton set 1, 2, its power set is going to contain the empty set, singleton 1, singleton 2, and the set itself, 1, 2. So you'll notice here that the elements are no longer just the numbers 1 and 2, but in fact the singleton sets 1 and 2. So the elements in a power set are sets themselves. Now let's do some examples involving Cartesian products and power sets. The first exercise defines 3 sets A, B, and C, as well as their universal set U, and we're first asked to find A cross B. So we remember that when we're trying to find A cross B, we're going to take ordered pairs where the first element in the ordered pair comes from the first set, in this case A, and the second comes from the second set, in this case B. And generally it's going to help to be a little bit orderly about this. So you'll see how I'm going to write this down. My first ordered pair, I want to take the element 0 from my set A, and I'll say 0, 2. That's one ordered pair, one element in my Cartesian product. And then I'm going to take 0, 3. Then I'll move on to the next element in A, which is 2. So I'll take 2, 2 and 2, 3. And then moving on to the next element in my set A, I'm going to do 3, 2 and 3, 3. Then if I'm not sure if I got them all, I can always count in the end. I know that the cardinality of A was 3, the cardinality of B was 2, so the cardinality of my Cartesian product should be 6, and I do have 6 elements, so I've got them all. Now let's look at B cross A. So now the ordered pairs, the first element is going to come from B, and I'm going to, again, try to do this in an orderly fashion. I'm going to start with 2, and then use all of the components from A as my second component. So 2, 0, then 2, 2, then 2, 3. Next, I'll use the number 3 from B, and 3, 0, 3, 2, 3, 3. So I make sure that each element from B gets paired with each element from A, and again, I have 6 elements. Now we can pause here and notice that these are not the same. I do have some elements in common, like 2, 2, 2, 3, 3, 3, and 3, 2. Those are the same in both sets, but that's sort of just a coincidence. I can also clearly see that I have some that are not the same. So we want to note here that A cross B is not, in general, equal to B cross A, and we'll explore that a little bit more coming up. Well, let's do C. We want A cross B cross C. So now I'm looking for ordered triples, where my first element comes from A, then the next from B, then the next from C. So again, I'll try to be orderly. I'm going to take 0 from A, 2 from B, and 1 from C. That's an element. I'm going to keep 0 and 2, and now from C I'm going to take 4. That's an element. Then I can take 0 from A, 3 from B, and 1 from C. 0 from A, 3 from B, and 4 from C. So these should be all of the possibilities for starting with 0. So I'll move on and then start with 2. So I'll take 2 from A, 2 from B, and 1 from C. 2 from A, 2 from B, and 4 from C. 2 from A, 3 from B, and 1 from C. And so on. Then starting with 3, I keep going. Again, I'm making sure to do this in an orderly fashion so that I don't get confused and have to work a lot harder in the end. Now, I count that I have 12 elements here, so I want to double check. I know that my cardinality should be the cardinality of A times the cardinality of B times the cardinality of C. So it should be 3 times 2 times 2, and that is 12. So we've got them all. What about the universal set crossed with the empty set B? Well, I'd be looking for all ordered pairs where the first element comes from the universal set and the second element comes from the empty set. But the empty set doesn't contain any elements, so there are no ordered pairs that can be formed that way. So the cross product of any set with the empty set is going to give me an empty set. Now I have A cross A complement. So since A is 0, 2, and 3, and I know my universal set is 0, 1, 2, 3, and 4, that tells me that A complement is 1, 4. It's everything in U that was not in A, which just happens to be the same as the set C. So A cross A complement will be 0, 1, 0, 4, 2, 1, 2, 4, 3, 1, and 3, 4. Perhaps one interesting thing to note here is that because it's the set crossed with its complement, we're never going to have an ordered pair where the two numbers are the same. Okay, moving on. F asks us to do B squared, which we know is B cross B. So the set 2, 3 crossed with the set 2, 3, that should be 2, 2, 2, 3, 3, 2, and 3, 3. Whereas G has asked us to do B cubed. So I'm going to be, again, looking for ordered triples. How many of them? Well, it should be 2 times 2 times 2, 8 of them. So let's start with, I'm going to take 2 from my first copy of B, 2 from my second copy of B, and 2 from my third copy of B, then 2, 2, and 3. Then I'll take 2, 3, and 2, changing now the middle one, 2, 3, and 3. And then I'll change my first one to 3, and I can have 3, 2, 2, 3, 2, 3, 3, 3, 2, 3, 3, 3. And I have 8 different ordered triples, so I know that I must have gotten them all. Now the last example is a bit more interesting because it's asked us to do B crossed with the power set of B. So off to the side, let's go ahead and make sure we know the power set of B. That should be the set of all subsets of B. So first of all, it contains the empty set because that's certainly a subset of B. Singleton 2 is a subset of B. Singleton 3 is a subset of B. And B is a subset of B. Instead of B, I could have written the set 2, 3. But you'll notice here that the elements of my power set, again, they're no longer sets. They are, in fact, they're no longer just the numbers 2 and 3. They are the sets singleton 2 and singleton 3. So if I want to take the Cartesian product of B with its power set, my first element will come from B, so I can take 2. My second element will come from the power set, so it will be a set, and that's okay. These ordered pairs don't have to be ordered pairs of numbers. In this case, the first element will be a number, and the second element will be a set. So I can have 2, the empty set, 2, singleton 2, 2, singleton 3, and then 2, the entire set B. I'm going to write the set out like that. Or I can start with the element 3 from the set B, and I can pair it with the empty set. I can have 3, singleton 2. I can have 3, singleton 3. And I can have 3, the entire set B. And again, I'll check how many elements do I have. I have 8. The cardinality of B is 2. The cardinality of the power set of B is 4, so that should be correct. Let's move on to the next example. It says, suppose that you are about to flip a coin and then roll a die. Let A be the set heads, tails, and B be the set 1, 2, 3, 4, 5, 6. So this should be a 6-sided die. Then it asks, what will be the cardinality of A cross B? So you'll notice that the set A doesn't contain numbers. It contains words or outcomes of flipping a coin, but that's all right. I can still count the number of outcomes. So the cardinality doesn't so much have to do with what types of objects are in the set, just how many objects. So I know that the cardinality of A cross B should be the cardinality of A times the cardinality of B, because they're both finite cardinalities. And in this case, that's 2 times 6, 12. Then it asks, how would we interpret the set A cross B? Well, if we looked at the set A cross B, they would be things like, I could have heads, comma, 1. That would be an element. I could have heads, comma, 2. And so on. Heads, comma, 6. Then I'd have tails, comma, 1. And so on, all the way up to tails, comma, 6. So this is what an element in the Cartesian product would look like. It would be an ordered pair where the first element is either heads or tails, and the second element is an integer between 1 and 6. So the interpretation of that, I'd say the set A cross B is the set of possible outcomes for the process of first flipping a coin, and then rolling a 6-sided dice. So if we just did that once, we flipped one coin and then we rolled one dice, then any of the elements in this Cartesian product could be our potential outcome. All right, let's see the next exercise. List all 2-element sets in the power set of ABCD. So again, the power set of ABCD is all of the subsets. So I'm asked to list all of the subsets of ABCD that have 2 elements. So that would be the set AB. That's a 2-element subset of ABCD. Maybe the set A, comma C, A, comma D. Or I could have B, comma C. I could have B, comma A, but I know that that's the same as the first set that I wrote down, so I don't need to write it. But I didn't write B, comma B, so let's write B, comma B. Nope, I apologize. B, comma C, and B, comma D. And then I could have C, comma D. So since the element B is just there once, I couldn't write B, comma B. Because they're not ordered pairs, they're sets. We don't want to write the element twice. We only need to count it once. So these 6 elements should be all possible 2-element subsets in the power set of ABCD. Next, it'll ask us to list all of the 3-element subsets. So in a similar orderly fashion, I'm going to see what combinations I could have. I could have A, B, and C. Or I could have A, B, and D. Or I could have A, C, and D. Or I could have B, C, and D. And that should be all of them. If I wasn't sure that I had gotten all of them, I could simply write down the power set of A, B, C, D, and then pick them all out. But that should definitely be all of them. The next question is, how many 1-element sets are there if in the power set of A if the cardinality of A is n? Well, we can think about our example that we were working out above, the set ABCD. If I was asked, which I was not, but if I was asked to do the one element sets, then what would they be? I could have singleton A, or singleton B, or singleton C, or singleton D, right? I could have 4 different singleton sets because there are 4 different elements. And the cardinality of ABCD is 4. So the same should apply here. If we have a finite cardinality of n, then in the power set of A, there will be n singletons. Next, we're asked, a person has 4 coins in his pocket, a penny, a nickel, a dime, and a quarter. How many different sums of money can he take out if he removes 3 coins at a time? So we have a word problem. Let's convert it into a problem about sets. I'm just going to give this set a name. I'm calling it M for money, but you could call it whatever you want or not give it a name at all if you want. And inside this set, I'm going to put penny, nickel, dime, and quarter. I was told that he has 1 of each in his pocket. So I'm just going to list them this way. This is the set of all the coins he has in his pocket. And the question is asked, how many different sums of money could he take out if he just pulled out 3 coins somewhat randomly? That's the same question as finding the 3 element subsets of the set ABCD. Instead of ABCD, if I had written penny, nickel, dime, quarter, then this would be exactly the scenario that we're talking about. So let's write those down. We could have penny, nickel, and dime. Or he could pull out a penny, a nickel, and a quarter. Or he could pull out a penny, a dime, and a quarter. Or he could pull out a nickel, a dime, and a quarter. And it doesn't matter which order he pulls these out in because we were simply asked about the different sums of money. So this should be 16 cents. A penny, a nickel, and a quarter would be 31 cents. A penny, a dime, and a quarter, 36 cents. A nickel, a dime, and a quarter, 40 cents. These are all different sums of money. So there are 4 possibilities. Now in question 7, we have interesting sets. Again, reinforcing the idea that the elements in our sets don't have to be numbers. Here we have the set A is plus, comma, minus, and B is 0, 0, 0, 1, 1, 0, 1, 1. So these are sort of strings. And we're asked to list the elements of A cross B, so we know how to do that. We're going to form ordered pairs where the first element is from A. So I take plus, and I want to make sure plus gets paired with every element in B. So plus, comma, 0, 0, plus, comma, 0, 1, plus, comma, 1, 0, plus, comma, 1, 1. Then I take minus as my first element, and I do the same thing. I make sure that minus gets paired with every element from B. And these are my ordered pairs. So that's my Cartesian product. How many elements do A to the power 4 and A cross B to the power 3 have, respectively? So cardinality of A to the power 4, well, that should be cardinality of A cross A cross A cross A. And that's the cardinality of A times the cardinality of A times the cardinality of A times the cardinality of A, since the cardinality of A is finite, which is 2 to the power 4, 16. The cardinality of A cross B cubed should be the cardinality of A cross B cross A cross B cross A cross B, which would be the cardinality of A cross B times the cardinality of A cross B times the cardinality of A cross B. But each of these is a cross product, so that's the cardinality of A times the cardinality of B times the cardinality of A times the cardinality of B times the cardinality of A times the cardinality of B. And we know the cardinality of A is 2, cardinality of B is 4, so this is going to be 2 cubed times 4 cubed, or in other words, 8 cubed, which is 512. The next question, again, we have sets containing non-numerical objects. We have a dot, a square, and a cross-looking thing. We're asked to list the elements of A cross B and list the elements of B cross A. The parentheses and the comma in an ordered pair are not necessary in cases such as this where the elements of each set are individual symbols. So what it's saying is that instead of writing like we did before, plus comma 0 0, because I just have symbols and there's no confusion about what goes where, I can drop that notation. So I'm going to write it like this. I'll have A cross B, and that's going to be equal to the set of dot square, comma, dot circle with a line through the middle, comma, dot dot, then square, 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 circle with line through the middle, and square dot. So you can see instead of using the parentheses and the commas for the ordered pair, I've just dropped them because it's clear that the first element is coming from A and the second element is coming from B. So then I have cross square is an element. The cross with the circle with a line through it is an element, and the cross with the dot is an element. And I can count. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 times 3, that should be correct. Then I'll do the same for B cross A. B cross A is going to be square dot, square, 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 cross, and so on. I'll list them all out. Dot, 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 square, and dot, cross. Then it says, identify the intersection of A cross B and B cross A for the case above. So looking through these sets, I definitely see that they have some things in common. Dot square, dot dot, square square, square dot. So all of those things are the same. And we remember that for the other elements, the order matters. They would be ordered pairs. We just dropped those parentheses. So they're not the same element. But these are in common. So this is A cross B intersected with B cross A. Looks like it's going to be the set dot square, dot dot, square square, and square dot. Then it says make a guess at a general rule for the intersection of A cross B and B cross A, where A and B are any two sets. So what I notice about the dot and the square is the reason that they show up in both is because dot and square are in both A and B. Because we know that the order matters, so when I'm looking at A cross B, this is coming from A, and this is coming from B. I have the same element in B cross A, except this dot came from B, and this dot came from A. But they're the same element because the dot was in both B and A, and the square was in both B and A. So my guess for the general rule is going to be that anything that's in the intersection of A and B crossed with anything that's in the intersection of A and B is going to end up being in the intersection of their cross. Finally, we are asked, for any two non-empty sets, when are A cross B and B cross A equal? Well, if A cross B is equal to B cross A, then I know that A cross B intersected with B cross A should be equal to A cross B, also equal to B cross A. Why is that? The intersection of two sets that are equal, remember intersection is any element that belongs to both. If they have exactly the same elements, then the set of elements that belongs to both is going to be just the whole set. So we can call it A cross B or B cross A. They're equal, so it doesn't matter. And then this intersection is the one that we were working with in the previous problem. So if this is true, that the intersection is equal to A cross B, then we would know that A cross B is a subset of B cross A. Why is that? Well, the intersection is A cross B. And the intersection is always a subset. So if I had two other sets, let's say I have C and D, then the intersection of C and D is always going to be a subset of C, and the intersection of C and D is always going to be a subset of D. So we just know that from our section on intersections and unions. So if the intersection is A cross B, then that means that A cross B should be a subset of A cross B and a subset of B cross A. But if A cross B is a subset of B cross A, then A is a subset of B, and B is a subset of A. And that's exactly what is required for two sets to be equal. Since A is a subset of B and B is a subset of A equals B. So I would suggest that in order for A cross B and B cross A to be equal, we'd have to have A is exactly equal to B. Otherwise, because the order matters, we're never going to get the cross products to be equal. And that looks like the last exercise for the lesson on set theory.